All right. Hi, everyone. Thank you for attending our virtual lunch talk this month. I want to introduce Howard Shrobe, one of our principal research scientists at CSAIL. In this talk, using AI planning to evaluate cyber vulnerability, Howard will outline how AI planning techniques can be used to assess the vulnerability of enterprise systems, how computer systems work, and how attackers think about forming their campaigns. Howard will also provide some examples that are inspired by real-world attack scenarios. Just in a housekeeping issue, please feel free to send me any questions you may have, and I will ask them at the end of the presentation in the chat. And with that, please feel free to take it away, Howie.
Okay. So this is a talk about research that I've been involved in for quite a very long time now. I think the original work on this took place in a DARPA program that I published a paper on, possibly in the mid to late 90s or early 20s. So it was one of the first papers on this kind of using planning techniques or other kinds of computer science technique to automate the process of developing possible attacks on an environment. So what I'm going to do is start with a real world example and take a look at it, and then we'll transition from that into what our system actually looks like and what it can do. I should also try to be honest about what it can't do at the moment, because there's probably more that it can't than what it can. So let's start with this real world example. In 2015 and 2016, in December of both years, if I remember correctly, there was an attack on the Ukrainian power grid in the city of Kyiv. And it took out power to a significant chunk of the city for about half a day in both cases, if I remember correctly. It's believed that this attack was launched by cyber hackers from the Russian government, but that's always hard to prove. So here's, a statement of background. So this focuses on the first one in 2015. So this regional electricity distribution company reported service outages. 23 substations were disconnected for up to 3 hours. And interestingly enough, the way they recovered from this attack was that all of the relays that connect the generator to the distribution network have manual overrides. And so they actually recovered by manually overriding things rather than by recovering from the cyber attack. 250,000 customers lost access, and the Ukraine government, and for that matter, US officials and most cyber experts believe this came from Russian security services. If you take a look at how this happened, there have been more sophisticated cyber attacks, but this is a fairly typical one. So the first step of this was emails were sent to a variety of people who worked on workstations within the company, but not necessarily within the operational parts of the company. And these were phishing emails. They had attachments that appeared to come from some higher management person in the company, and asked people to click on the link that allowed the attachments to be launched in an application. The attachments were, of course, malicious and managed to establish a foothold within the workstations of these people. Now, the workstations were on what's called the IT part of the network as opposed to the OT, the operational technology. The first thing that happened then was downloading of a package of malware called Black Energy, which installed a keystroke logger amongst many other pieces of malware, and proceeded to sort of mine around the system to try to pick up credentials. The key point in all of this was capturing the credentials of a system administrator, and that was done with a very clever technique, which, since they already had a keystroke capturer installed, what they did was use one of the tools within Black Energy to disable one of the workstations. which then would signal a system administrator to come to try to repair the system. When the system administrator logged in, the keystroke logger captured his credentials and exfiltrated them. So now the attackers could operate with the privileges of a system administrator. That allowed them, amongst other things, to get across the VPN, virtual private network, which allowed them to log into the operational technology part of the network from outside. So at this point, they were actually operating as legitimate users using the stolen credentials and the VPN access that they'd gotten. What they then did was, to scan the network, exfiltrate host and device information. This went on over a very long period of time, maybe half a year even. And eventually they had installed enough malware in the right places to be able to open the breakers that connected power distribution to the distribution network, and also to disable a link that connected the computer network to the serial ports that actually operated those breakers. So after they opened the breakers, they literally physically damaged by cyber means this bridge between the two parts of the system, which meant that the operator's console could no longer actually control the breakers. On top of that, they had also locked the operators out of the operator console, which they had access to. And finally, they simultaneously launched a denial of service attack on the phone network so that the system administrators and the operators couldn't even communicate with one another. So this was a pretty sophisticated attack, even though we've seen attacks that have higher levels of technology involved in them. Particularly those of you who are familiar with Stuxnets know that that involved a more sophisticated campaign. So this is just summarizing the rest of what went on. As I mentioned, they used this interesting privilege escalation technique, which was to install the keylogger, filled up the disk with junk files, I think overwrote the boot partition also, which called in the system administrator. And then when he logged in, they captured the credentials, and which then allowed them to act legitimately as if they were actually a legitimate system in. Now, there are a number of things that enabled this. First of all, there's a surprising amount of open source information available about the kinds of technology that's used in power distribution. There are good reasons for this. It helps, interoperate between different vendors, but it meant that the attackers could get technical information relatively easily. The VPN, which allowed them to get from the business network into the operational technology part of the system, didn't have two-factor authentication. So having stolen a credential, that was all they needed. The firewall didn't prevent remote administration. There didn't seem to be any capability for monitoring what was going on in the network. ICS here, by the way, stands for Industrial Control Systems. And the attacker in this case was operating within the system for up to 6 months. Part of this attack was, quote, low and slow, as we say in the field, meaning when they downloaded their malware, they did this at a very low rate and in a very distributed way, making it difficult to detect that this was going on. But the key point seemed to be that this company didn't really have in place any sort of self-monitoring technology that might have been able to pick up that something was going wrong. Now, those enablers are pretty common. And so I think the summary lesson, just looking at this case study, is that vulnerabilities are pervasive. There's a general rule of thumb in computer science that says there's a pretty constant ratio of bugs to lines of source code, independent of almost everything. So it doesn't matter what source language you're writing in, take the number of lines of code and multiply by some factor, and you'll get the number of bugs. And there's another fairly standard ratio of those bugs, which ones are vulnerable, are exploitable. And so roughly speaking, the bigger the system, the bigger the attack surface. Now, the second thing to notice is that we often tend to focus on a single exploit, something that, you get a phishing email and that compromises your system. But in fact, what's really going on here is a campaign. involving multiple exploits, many steps, and in this case, something that persisted over a period of 6 months or possibly more. The thing that is clear is that when you start to think about, well, how do the attackers think about this? It's very much of a planning kind of exercise. They know where they want to get. They wanted to be able to turn off the power grid. But to get there, they needed to get into a part of the system that is not directly accessible from the outside. And so they reduced that initial goal to sub-goals. Well, if we could get into the IT part of the network, and if we could bridge from there to the OT part of the network, then we could do what we wanted to do. And so now we've reduced ourselves to 2 sub-goals. How do we bridge between the two? Well, that's getting VPN credentials. And how do we get in from the outside to begin with? That was by sending a phishing email. And of course, there are many other ways of doing each of these things. So the lesson is that there is a way that attackers think, and it corresponds pretty much to the way AI planning tools work. That is by reducing goals to sub-goals and eventually down to actions that can achieve those sub-goals. It's also the case that one of the big lessons of this and many other penetrations is that we need to be building systems that self-monitor, that can pick up the signs of attacks at system speed, because they often evolve faster than a person can respond. But they also may take a very long time to set up. And so if we can do the monitoring right, we may be able to intervene before the truly awful things happen. So I've developed a big picture idea that we called AUDRAP, which was a tremendously tortured acronym for some of the different types of technology in this model. And roughly speaking, the things in red here are things that are based upon a system model. The things that are blue are things that are intended to recognize attacks that are going on. And the big picture is that if we had a model of how a system is intended to behave, we could instrument it to feed information out from the application software to something that would compare what the system model is predicting should happen to what actually happened. And when those disagree, we have enough information from the system model to diagnose what went wrong. That information can help us do 2 things. One is it can help us figure out what parts of our system we can still trust. Are there subsystems that weren't compromised that can still give us useful work? And if so, can we recover in a way where we continue to do useful work by using the parts of the system that are more trustable? The other thing that this red section does is, in effect, it functions as a sensor. So it can pick up indications that things are not going well, and we can compare those to some attack plan using a standard set of AI techniques that go by the name of attack plan recognition, or sometimes are referred to as inverse planning, depending what communities you're talking to. So that recognizer can be fed by all kinds of conventional sensors, intrusion detection tools, and so on. But it's also fed by a library of attack plans, things that we have already figured out would be possible ways of going after this system. And those attack plans come from somewhere. They could be created by hand, but they could also be generated automatically. And that's what the rest of this talk is going to be about. So I coined this term computational vulnerability analysis, which alas, no one else has ever picked up on. But generally, there are a variety of projects that have built various kinds of attack plan generators using either standard kind of planning technology as I did, or sometimes using model checking tools that can also generate paths through a description of the system. So what informs any of those approaches are 3 main things. One is some background knowledge about how a system works, how computing and communication systems work. As is, the models that a model checker would use, or the background knowledge that a planner would use, has to include an understanding of how computing systems work, how they're decomposed into parts, which parts depend on each other, what the dependencies are like, and so on. The second thing that they depend on is, I actually jumped ahead just a little bit, but is a knowledge of the environment. So we're trying to defend some enterprise computing environment. Presumably, we know something about that environment, like what are the systems, where are the firewalls, what's the subnetworking structure, what parts of the system really constitute the crown jewels. So those are the systems that an attacker might go after because they have the credit card information, the money, the battle orders in a military context, or the goodies in this case is the power plant in the thing we looked at. So this is the general picture, given a model of the environment, an ontology that tells us about how systems work, and an understanding of how attackers think. Our planner then generates a library of potential attacks against this, which can be fed to an attack plan recognizer for online use, but can also be used as a way of auditing our system and thinking about where its weaknesses are. And the goal here is to be as complete as possible so that we can possibly raise things about the vulnerabilities of a system or an enterprise environment that might not have occurred to the people whose job it is to defend it. So let me go into a little more detail. This is sort of the output of what our planner can produce. The things in blue boxes here are goals and sub-goals. The things in red boxes are actual actions you can take. And this complicated directed acyclic graph is showing all the different ways that you can do the sub-steps of this plan. Those are OR nodes. And the things that you have to achieve in concert, those are the AND nodes of this AND/OR graph. I'll get back to the virtue of this towards the end of the talk. So how do we do this? As I said, we're relying on some background knowledge. So our system knows a modest amount about how computer systems are structured and how they work. We're given a model of the environment that we're trying to protect. And then we analyze how properties depend on things. So we start off by asking, can you compromise this useful property of some resource within this overall environment? And the way the thinking goes is to take advantage of this model of how computer systems are structured. So we know things like there are operating systems and there's hardware and software and file systems and things that control access to the system and so on. Even going further down, we know that there are things like privileges and permissions, and you can only access things that you have the appropriate permissions for. So as I said, we know a modest amount about how computing systems are built and how the different parts depend on one another. We're given a model of the system topology in terms of what workstations and servers and so on there are, what software suites they're running. Ideally, this would be fairly complete, but in practice, nobody ever knows actually what they have. But we usually know at least what are the things we really care about, and those are the ones we want to protect. And we also know things about what the firewalls and packet filtering and restrictions are in terms of how you can get into the network and how you can't get into the network from the outside. So we break our knowledge down into several different levels. Some of this is extremely abstract, which is then refined down to more specific knowledge. For those of you who know about MITRE's work on the attack matrix, that's ATT_CK, a lot of what we have in our system corresponds to the text that's in their attack matrix. They have what are called tactics, techniques, and procedures. We have some things that are a bit more abstract than that, but a lot of what we have corresponds to what's in attack. So these include things like at the very abstract level that, influence follows flow of control, flow of data, and structural decomposition. So if you're trying to achieve some goal, maybe you can look at ways of influencing that by this flow of control or control of data and sort of move back through the system. If you want to, I'll show you some rules that are in our system that are exactly that, which says, if you want to affect this property of this component, and you can't get there directly, what you want to look at is what produces inputs to it, or what controls the control flow to it. Or does it break down into pieces, one of which is more susceptible than the whole thing as a whole looks to be. But then, as I said, we have lots of specific knowledge, which corresponds largely to those lower layers of the attack matrix. So if you take a particular operating system like Windows, but you can pick on Linux or Mac OS as well, there's lots of specific things that you can exploit. For example, in Windows systems, it's very common that there's a domain that unifies a bunch of different systems, and privilege management is centered there. Often the domain controller directories have within them files that have scripts. Some of those scripts actually contain credentials. That's something you can exploit, and you maybe could figure that out from first principles, but it's better just to know this. And so, if you're trying to do privilege escalation in a Windows domain, that's a method you might use. So we know things at all of these different levels. As I said, one of the key notions in the whole system is dependency. What depends on what and how it can influence one another. So our system is built out of these planning operators, which are things that reduce higher level goals to a collection of lower level goals, sub goals, and actual actions that can be taken. And at the top level, as I said, this is rather abstract. So it says things like, if you want to affect a desirable property, get control of some component that contributes to the delivery of that property. So at that level of abstraction, you could reduce that to something like, well, if you wanted to affect the performance of a system, one thing that's very much involved in that is the scheduler. And so it would tell you, well, think about ways you might affect the scheduler. And one of the inputs to the scheduler is things that add workload. So find a way to add new workload. And so you can reason at that level, and then eventually get down to more concrete levels where you start thinking about actual tactics, techniques, and procedures. I'll run through a few things that our system knows about. Some of these are the very low level things, like some particular web server is vulnerable to buffer overflow attacks. I was just looking at a slide the other day that says, even today, when you look at the vulnerabilities that are known in a variety of large scale systems from Google, Apple, Microsoft, 70% plus or minus a little bit of those are this style of attack, memory safety violations. And what this means is that, if this web server is vulnerable to this kind of attack, then you can use it to take control of the web server process. And that could be very valuable because lots of other things are affected by that. As I mentioned, this idea that the scheduler affects performance. And so if you're interested in performance, you could think about, how do I affect the scheduler? One way that is, scheduler has policy parameters. You could possibly change those. In order to do that, you have to get access to a file in which those parameters are stored. And so you would backward chain to think about, how do I do that kind of activity? Another way to affect the performance would be to load the system up with jobs. And so all you need to do is find a way to create lots of jobs. That might chain you back to the idea of get logged in and launch a bunch of jobs. But it could also backward chain you to, well, if the system's running some sort of server that is open to the outside, you can just connect and flood it with job requests, which is a standard way of doing more targeted denials of service. Another general approach is to try to control the inputs to something. As I said, the workload is conceptually an input to the scheduler. So if you can affect the workload, then, which you can do through whatever it is that lets jobs get started, then you can affect the performance of the system. Variety of different ways to do this. If you can't, if you want to affect an input, one of the ways you would think about that is find some component that produces that input and then find a way to take over that component. The system knows a fair amount about access rights. It has a fairly general framework for expressing this. The model is sort of the general access control matrix kind of idea. That is, for every object that's known in the system, there are a set of operations you can perform on that. And those operations require certain capabilities in order to be performed. And principals, that is users or processes, have possession of certain capabilities, which would allow them to do these operations, or in the lack of that, prevent them from doing that. So by modeling this, which we tend to do through an abstraction called an access pool, that's the equivalent of something like domain or common user login control over an ensemble of machines. part of the specification of the environment is to spell out who needs what. But then a lot of what our system knows is ways to get access rights that you don't already have. So one way to do that is to find some process that already has the capability you're looking for. So take the web server, for example. It may have read and write capabilities to a great deal of the system. If you can find a way to get control of that process, you can use that to get these capabilities and then escalate your privilege. Another way to do this is to find some user who actually has the privileges you're looking for, and then find some way to log in as that user, or to launch a process with that user's capabilities. Again, this will chain back to other things you might do. And there's a variety of ways of logging on. One of those is by guessing passwords. Another way is by getting some presence on the network and sniffing password exchanges. Even when they're encrypted, sometimes that's enough to help you actually get the real password. Another way of doing this is by, if you can get access, modification access to the password file, you can change somebody's password from under them to something you know. And then finally, as I mentioned, often there are files around that typically for sys administrators that contain password information in them. And so by being able to just get some read access to appropriate directories, which interestingly enough are usually not protected, you may be able to scrape password information out of there. Another thing our system knows about is a notion I called residences and formats. So if you think about it, any piece of software resides in several different places over its lifetime. It could be running in main memory as actual, bits. It could be in a boot or a linked executable file. It could be in paging files, but it also exists in other formats: source code, linked format files, and so on. And these different formats of the system and the different residences, there are migration processes. Source gets turned to binary by compiling. Binary gets turned into executables by linking. Linked executables get turned into code in memory by loading. So the reason for having our system know that is a general attack method which says go upstream in the life cycle to someplace where you can get access, find some residence and format of the component, and modify or observe it depending on whether your goal is to take over or simply to learn something, and then cause or wait for it to migrate and transform into the format where it's actually executed. I should mention that the recent SolarWinds hack is a good example of this, where the attackers moved back from a variety of targets they were interested in to a supplier of software to all of those targets, and then figured out how to compromise that. So that as the software migrated through software distribution channels, it then infected all of the machines that the attackers were really interested in, because they weren't actually interested in SolarWinds at all, as far as we know, except as a vehicle for getting to the other systems. As I said, this idea of formats and transformations goes along with that. And the basic strategy is to go upstream and see if you can take control of something there. Another set of things our system knows about is what's referred to as lateral motion, which is one of the top tactics in the attack matrix. So often your original target, like the power distribution network in the Ukraine power grid example, is not directly accessible from where the bad guy is sitting. But the bad guy can get to someplace else, which is the foothold. And so our system has a strategy in it that says, if you can't get to the original target, then find some foothold that does have the ability to get to that target, because it's inside the enclave and there's implicit trust extended within the enclave. There's a rather good example of this in the attack against the Target chain of stores, where the initial penetration was not into Target's financial systems, but rather into the controller of their heating, ventilation, and air conditioning system, which happened to reside on the same network as the other systems. And therefore, from its position, could access the real target, which was the credit card database, which was inaccessible from outside. So lateral motion is this idea of making penetration to some place from which you can move, quote, laterally to the original target, or perhaps to some place that's at least closer to your original target. For those of you who might be curious what this looks like in a formal sense within our system, it uses this parenthesized notation that's common in the AI planning community, sort of, for those of you who know the Lisp programming language, it grew out of that. And basically what it says is we have methods that say, here's a goal that you want to achieve. Here are some prerequisite conditions that govern whether this method is a reasonable one for your goal. And then it reduces this to a plan, in this case, a sequential set of steps of sub-goals to achieve remote execution on some foothold in some role on that foothold, and another goal to make a connection to that machine, and then post conditions, things that would be true after you had actually achieved this. In this notation, things with question marks in them are variables that get bound as the reasoning process goes along. As the note here says, this is similar to PDDL, which is the standard planning description language in the research community. Here's another one for remote execution. Interestingly enough, to get remote execution, you may need to get a foothold, which in turn requires you to get remote execution. So this backward chaining can sort of interleave between those two things until you eventually find someplace you can actually get to, and then a string of actions where you get remote execution on each of the intermediaries, which then serve as a foothold for getting remote execution on the next one, until you eventually are able to reach your target in a way that's useful for you in terms of the compromise you want to do. So here's an example, which is not exactly the Ukraine example, but was certainly motivated by it. Imagine we have three enclaves in our enterprise: an enclave of worker machines, an enclave of administrator machines, and an enclave of server machines. And the server enclave is running a, quote, high database. That's the more secure one, more protected one, and a low database, which is less protected. And the attacker's goal, sitting out in the wild somewhere, is to compromise the data on that server on the high database. Now, how does he do that? Well, by now it should be obvious. My answer is he needs a plan. And the point drawn in the picture is that he can't really get directly to the server machines. But the worker enclave is more permeable because, amongst other things, it will accept email. It might accept remote logins. There might even be web servers running on some of those worker enclave machines. And so you can imagine an attack which first penetrates the worker enclave, somehow gets to the administrative enclave, at least to get administrative credentials, which are necessary for modifying the high database, and then connects to the high database, again, through a more permeable connection, because the worker enclave is more trusted. That is to say, the firewall allows traffic through from the worker enclave that it would not allow through from the outside. So here's one attack plan we can generate. It says somehow log into one of the worker machines, install malware packages, keylogger and kill disk. This is based exactly on the Ukraine example. Cause the sysadmin to log into the compromised machine. That lets us capture the sysadmin's credentials. And then those credentials allow us to connect to the high server. And once we can do that, we can modify the contents of the high database. So one thing that's an interesting way of looking at this is that this kind of a plan is really a story in the normal sense of the word. It says, this is the way the bad guy's going to go at this. There are connections between the different pieces of the story. There are purposeful relationships between the steps of this. And in one of the DARPA programs I work in, this notion of being able to tell stories about attacks, as opposed to just being able to identify some exploit that took place, but to paint the bigger picture, the story of how the campaign is going to proceed. This notion has gained a lot of currency within the program. And in fact, everybody now talks about producing stories. So this is sort of a more readable graphical version of that kind of an attack plan, with the sub goals of, top level initial penetration, privilege escalation, exfiltration of data. This is from a slightly different example that we've also been working on in that DARPA program. And this resolves down to more specific actions, including in this case, some things that were fairly specific to the environment we were working in and to things that were typical of the Microsoft environment that was the test case for this. This is what our system actually produces in terms of output. As I said, the blue boxes are the sub-goals. The little green boxes are things that are relating sub-goals. So some of them say sequential. Some of them say reduces to, so a more high-level goal reduces to a single sub-goal. And wherever there are two arrows coming into a box that are not connected by sequential, that means either of these would work. This is a single attack plan. We generate a lot of these and then merge them together, which is where those OR connections start showing up. And what the OR connections mean is that any way I could achieve this sub-goal is good enough because it enables the rest of the plan. And where the sequential connections or parallel connections are also allowed, it means we have to achieve both of these sub-goals in order for this super goal to be achieved. Here's another example I just want to mention because it's from a sort of different domain. This was from an exercise we did with the Naval Postgraduate School a couple of years ago. It was held over a weekend at MIT. They had put together a system that they called Trudy, which was a mock-up of the computational and control and communication equipment that you would see on a large commercial ship, ocean-going ship. And it has a variety of sensors, an autopilot process, GPS receivers, as well as some conventional information technology, because these ships go out on missions for months at a time, and the people who are on board want to have email connections and actually cell phone connections back home. So again, you can imagine campaigns against a system like this that would penetrate more directly through that cell phone modem, the IT network, and then work its way through to affecting the control systems that are actually steering the ship. This is just a quick video of our system in action. So we're loading in a model of some environment, which is this Trudy network I just showed there. And then we ask it to find plans for compromising the autopilot process, the accuracy of the autopilot process that's running on the autopilot computer. And we produced, I think, 6 or 7 plans. This is showing one of those. And you can see, as this scrolls around, going from higher level goals down to lower level goals. In this case, the plan's relatively simple. I think that might have been the end of it. Nope. Here's another plan. Involves a sort of slightly different way of achieving some of the first goals. This one winds up using its compromise of the central computer in this whole system to inject false data onto the control bus that the autopilot's sitting on. The other attack wound up compromising the charts that it does its planning from. And we can merge these plans into one common plan, merge plan, whoops, which looks like this. And this is an eye chart. I obviously don't expect you to read it. As I said, these have combinations here that are both OR nodes. You can barely see that there. This means that there's a goal here that could be achieved in more than one way, either that way or this way. And we've merged this all together because this allows us to now do the thing we're really interested in, which is thinking about how we might protect our system. And so here we finally get to the payoff of the talk, which is, what's the use of this in auditing? Well, our goal is to generate as many attack plans as we possibly can, given our enterprise description. Because we're trying to generate every plan possible, our planner is actually not very sophisticated. It's not using clever heuristics. It's just trying to be complete. Those are merged into an and/or directed graph. And now the key insight is that if you can find a set of mitigations that remove all of the OR branches into a node, or at least one branch into an AND node, you have prevented the attack from going on. And so the defender's role, now having generated all the possible ways of attacking the system, is to figure out what mitigations they can take to do just what I said, which is to cut off all possible ways of achieving some sub-goal, and at least one critical sub-goal of the top-level goal, such that you can't achieve that. It also helps you in monitoring because it's sort of giving you a plan for how the attacker would be moving through the enterprise. And you may be able to make better observations at some of those points than others. So in summary, the key insight I wanted you to remember is that attackers are interested in campaigns, not just individual exploits. They want to put exploits together to achieve their real goal. And to do that, they reason about the dependability, the dependencies, the accessibility, and how various things control one another in pursuit of their goals and sub-goals. That is very well modeled by classic AI planning techniques, which will then let us figure out where the potential weaknesses in our enterprise computing environment are and help us guide in making choices about what mitigations to employ. So I've talked for about 40 minutes and be happy to answer questions.
Thank you so much, Howie. We did get one question.
Uh-huh.
This person really likes the idea of taking advantage of the similarities between AI planning and attack strategies. They want to know if you've seen any usefulness or challenges in using a generative adversarial network or something similar in this type of work. And they mention it could be able to generate all kinds of attacks given a set of characteristics and can be used to thoroughly train a neural network.
It's a good question. I'm not sure whether that's exactly the right technology. We all have our biases, right? And I'm an old-time AI guy. So my biases are much more towards symbolic kinds of techniques. And particularly in the cyber world, our use of machine learning techniques, either more traditional ones or deep networks and things like that, they're somewhat bounded because they're fed information about what we've seen so far. And they do a modestly good job of being able to recognize small variations of things we've seen so far. But when an attacker comes up with a novel exploit or a novel campaign, these tools typically don't do that well on those because they don't have the training data to learn off of. So I think in some cases we have to resort back to more first principle kinds of reasoning. I'm certainly not opposed from an engineering point of view at all to being able to merge things that have different useful capabilities. Now, a different idea than what currently goes as generative adversarial networks is you can imagine this planner essentially as a generator. And now the question is, well, how could we try out the plans that this thing generates, which are still down at the bottom, relatively abstract. They aren't specific exploits. So there are two other things this could go along with. One is a variety of projects that have been used to generate exploits, low-level exploits. There's some very good work on that from a team led by David Brumley at Carnegie Mellon. We've looked at some of that work. And so you can imagine a much bigger tool that starts at the level we work at, gets down to the bottom level, which says, well, I need exploits of these kinds, some of which may be in standard toolkits. I should mention that the attackers are much better tooled up than the defenders are. For example, MITRE, who is on the side of the angels, there's another system they've built called Caldera, which is a toolkit of a variety of attacks that correspond very much to the levels of the attack matrix. So one idea is to go automatically from our attack plans to things that are already instrumentable through Caldera, and to use those as tools for seeing whether we can actually push an attack through on our own environment. So sort of automating a penetration tester. Of course, you have to be careful because you don't actually want to trash your own environment. In the end, you want to say, yes, I could go in there, but I'm not actually going to ruin everything. And the other thing you could do is call on some of these automatic generation tools to generate exploits where you don't have anything in your current bag of tricks. And to me, that's an interesting approach to this kind of thing. It's not today's notion of generative adversarial networks, but it is a generative adversary, which plays the same role, which is helping us figure out, can the system we want to deploy be tricked by a bad guy? So it bears that similarity.
Thank you for that, Howie. Another question we received, this seems like this approach could be quite readily applied to more embedded system design and evaluation. Have you used the approach to look at decomposed embedded system, and what did you find?
Yeah, well, that example I gave you, the thing called Trudy, is an example of that. Um, it's, an autopilot system that's running on a ship. And we did find that there are ways of compromising it. In that case, the most obvious place of compromise, and this is not new knowledge at all, is the bus that all of the operational technology sits on in that system is the CAN bus, which is used in automobiles as well. And CAN bus is singularly unprotected. Any component that's attached to the bus can inject messages to any other component on the bus. There's no authentication of that. And so the plan that we developed was to penetrate the central machine, the nav, what's called the NavNet machine, which is this touchscreen Windows computer that connects both to the email servers, but also sits on the CAN bus. And so if you can penetrate that, you can inject messages on the CAN bus. For example, you can tell the autopilot that it's not where it thinks it is. And you can do that repeatedly in a way that will cause the thing to go off course. For people interested in that level of technology, there's some very disheartening papers that show that if you can do false data injection, or sensor spoofing, as it's also frequently called, there are ways of doing that that are optimal and stealthy, meaning that the defender can't tell that they're being hacked. And the reason they can't tell is, think of yourself as being in the matrix. That's the way I always like to explain it. If you're in the matrix, there's no way you can tell you're in the matrix because all your sensors are being fed by the matrix. So a control system like that autopilot, what it knows about the world is what its sensors are telling it. And the way the sensors tell it that is through the CAN bus. If you can inject messages on the CAN bus that say, no, you're not where you are, or alternatively, steer to someplace else, there's no way the system can tell that those messages are wrong. The qualitative insight into this is everything in the real world has a certain amount of noise. And all control systems try to deal with that noise by various kinds of predictive filters like Kalman filters. And there are a lot of standard techniques for telling whether your sensors have gone haywire by looking at some of the statistics of what those filters do. But you can live within the noise margin and systematically sort of jiggle the system off its course in a way that those tests for whether the sensor has gone haywire won't detect. There's some threshold they're looking for, and you can stay below that threshold and still screw the system up considerably. So as I said, that's sort of disheartening news because, I'm trying to be on the good guy side here. And I would like it to be the case that there are ways of actually figuring out that the system's been hacked. The general answer to that is that that's an architectural challenge. So if you had ways of architecting the system, for example, the thing wrong with CAN bus is there's no authentication. Well, don't do that. Have a different bus that's authenticated. Introduce more redundancy, introduce not only redundancy, but variation between the redundant pieces so that an attack that would affect one won't affect others. One of my colleagues, Bob Ladago, who used to work with me here at MIT, he's involved in another DARPA program called CASE, not to be confused with the one I'm in, which is called CHASE. And CASE is about designing secure systems. And they've used this same knowledge base and a planner of their own that's slightly different than mine to evaluate potential system designs for embedded systems. Think things that military people build. And the idea is at the design stage to pick up potential cyber vulnerabilities using exactly the same approach, and then to re-architect the system so that it's at least less vulnerable to those kinds of attacks.
Thank you. This might be sort of a follow-up to what you were just mentioning with attack detection, but what sort of tools and methods do you look for in determining thresholds for those attack detection?
It's a whole can of worms. Most of the things that are down there picking up the low-level signals, like somebody just did this exploit, they're statistical in nature. And so they give you, if they're at all decent, they give you some margin of error on how sure they are about what they think they've seen. And then the plan recognizers are also going to be probabilistic in the sense that they're trying to combine those numbers to maintain some model of how certain we are that things are going on. So typically you have a library of potential plans of some size, and the task is to figure out which of those is the most likely one at the moment. And if it is likely, what's the next thing that is likely to happen, particularly the next thing that's easily observable or easily preventable. So the recognition techniques are all more probabilistic in character. They're sort of a mix of the planning aspect of this because they're trying to recognize a plan, but you have to account for the uncertainty of all your tools, and that's why the probability starts entering into it.
Sounds good, thank you. We received one concern in this space is how to mitigate without having to mitigate in 1,000 different ways. Can this approach help in understanding broader approaches to mitigation?
Right. I've seen some work. In fact, I supervised a master's in engineering thesis a year ago that did some automatic mitigation. And it was in a very constrained context. The context was software-defined networks. And the automatic mitigations were changing some of the configurations of that network to cut off traffic that was potentially malicious. Now, part of the thesis was taking account of the fact that if you don't do this well, you're going to deny service to yourself. Because the easiest way to prevent all, malicious penetrations is to prevent any penetration. So if you cut off all network traffic, you won't get hacked, but you're a brick then. So he, drew on, classic decision theoretic ways of formulating this problem, where you're thinking about the cost of this mitigation, both in terms of what it might actually cost, say, in terms of, if the mitigation is put in a firewall, that costs you real money. If the mitigation has changed the firewall rules to prevent this traffic, that has an impact in terms of what services you can render. And if you can monetize that in some sense, put a value on it, you can then formulate this as an optimization problem of cutting off the, reducing your risk below some risk tolerance threshold that you have within a cost bound that you're willing to incur. And so that's one way of thinking of this. But I think, generally speaking, that framework of the problem is computationally very difficult. And so we need to look for ways of making it more tractable. The other thing is that often we're talking about different kinds of currency at the same time. So there's the cost of buying a piece of equipment. You can measure that in dollars. There's the cost of not providing a service, which is not so easy to measure in dollars. So you have to think about ways you can combine these that let you do the standard formulations. That general way of looking at the problem, though, I think is the right way, which is asking what is the cost to the defender of a particular kind of penetration. So should this campaign succeed, how harmful is it to me? And one thing that we've just begun to realize is that this is not exactly a zero-sum game, at least not a two-party zero-sum game. Think about the attack on Target, which stole a bunch of credit cards. Well, the credit cards have a value to the attacker of something like 5 cents a piece. So if you steal 100 million of them, you make some real money. The cost to Target of that was not the same because the credit cards are all insured. And so Target's actual monetary loss was not very large. Their reputation loss was pretty serious, but that decays quickly. And so when you think about, well, what's the valid defense that the defender might want to incur? That's not the same thing as what's the best attack that the attacker can launch. And so the defender has to think about how much they would lose and what's the relevant investment worth. This comes down to the question that CISOs, information security officers are always lamenting, which is when they try to get budget, the question they always get asked is, well, if we employ this defense, I know what it's going to cost. Can you tell me what it's going to gain? Right? How do we justify that investment? And generally speaking, it's hard to answer that question. But I think this way of looking at it, which is, well, there are these attacks which we could foresee as being possible. Some of those attacks we can put a cost on to us. And this defense, based on our analysis, will eliminate that attack, or at least make the work factor for the attacker much higher, and therefore the probability of success much lower, meaning our risk of that loss, combination of cost and probability of it actually happening, is reduced down. And so now we can monetize the investment. We're a long way from being able to do that very well, but I think that's the outline of what we ought to be thinking about.
Thank you, Howie. We have 2 more questions. I know we're approaching the top of the hour, if you have time.
Yeah, I do. I'll try to be quick.
Okay. One defensive strategy is to harden the nodes in the attack plan. Another is to add redundancy, a la fly-by-wire's use of 3 redundant sensors and requiring majority vote. To what extent is hardening a non-redundant system better or worse than adding diverse redundancy into a system?
Oh, God. My personal belief is that life would be a whole lot better if we didn't have such flaky systems to begin with. So I think I mentioned somewhere in the talk that 70% of the vulnerabilities that all the big players report are memory safety violations. Now, this is easy to say, but hard to do. If we hadn't programmed all these systems in unsafe languages like C, we wouldn't have most of the problems we have. Roughly speaking, there are 2 big portals of entry into systems. One are exploiting memory vulnerabilities, and the other is various forms of getting logged in when we shouldn't have been able to. The second one we can deal with pretty adequately through dual factor authentication. And the first we could deal with through what is admittedly a huge investment, but rebuilding our systems with safer technology. So my feeling is that if it weren't for the fact that it's costly and time consuming to do that, we would do that first and then think about now what sensors do we deploy, how much redundancy and diversity amongst those that we need. And because we're never going to fix everything. I'd like to think we could build inherently secure systems, but that's a long way off. But we could build much more secure systems which would reduce the need to pick up these attacks. And the economic analysis says if you can make the attacker work hard enough, they'll at least go and bother somebody else. So I think both of these are important things to do. If you're pragmatically trying to solve today's problems, being able to detect and prevent is better than, it's more accessible than building truly secure systems, which we're beginning to develop some technology for that, but it's a long way off still.
Thank you. And finally, to wrap up, this person back to Case and Chase. Have you ever pointed the 2 systems at each other to verify each of them?
No, they're both big enough things with many moving parts and actually are focused on slightly different parts of the life cycle. Case is aimed at the design side of the life cycle, and Chase is aimed at, the very real day-to-day problem of we're running huge enterprises and they're getting penetrated and the sysadmin's jobs is untenable. How do we provide them some help, which is what Chase is trying to do. Just to give you a scary number, my recollection, this is sort of qualitative, is that in one of the potential transition targets for that program, it's a DoD cyber ops center. They have around the clock system admins processing alerts. And I think there are 3 people on in each shift. So there are 3 teams of 3, something like that. Anyway, one of those 24-hour teams processes something on the order of 6,000 to 8,000 alerts per day. So we're just swamped in, alerts going off, many of which are completely spurious, by the way. In fact, most of them are. But these guys' problem, which I very much sympathize with, is how do they find the needle in the haystack? And so Chase is really focused very, very laser-like on that problem. And Case is a much more high-level thing of, can we in fact design the systems to be hard to begin with?
Great. Well, thank you so much, Howie, for taking the time today to speak with everyone. And for anyone else that's watching this presentation after, we're happy to connect if you have any follow-up
Yeah, yeah,
questions
absolutely.
about what you just watched. So
Right,
with that, thank you so much, Howie.
right. Take care. I see a bunch of my old friends logged in here also, so thank you guys for joining too.
All right. Well, have a great day, everyone. Thank you again.